All right, everybody. So my name's Phil Williams. I work for Canonical. I had this realization last week. I've been doing the storage thing for like 18 years. So now I feel really old. I also had a second revelation that I've been working with Ceph for about 8 years. I've started products around Ceph, a bunch of different organizations taking over products, turn them into new things, build new tooling around them. I have a technical background. Now I'm very much in a product manager kind of role. I still work really heavily with our engineering team, and then sometimes actually like to play with the stuff that we build. So this is going to be a bit of a story around how we've been enabling QAT in Ubuntu and what that means for Ceph. So I think everyone here who knows and loves Ceph probably agrees that the best thing about it is it's hardware agnostic. But sometimes there are certain pieces of hardware that we can actually we can take advantage of. So certain accelerators, some of the CPU extensions, and that involves work in Ceph to take advantage of those things. And the thing that I want to talk about today is Intel's QAT. So that's Intel's Quick Assist technology. It's kind of an all-encompassing thing. It does a whole bunch of different stuff. There's offloads for crypto pieces of work, for keygen, compression, and a ton of stuff around wireless algorithms as well, so for like the telco industries. It's highly configurable. There's a couple of ways of using it. You can use like a dynamic service, so you have a service running on a machine, and the software interacts with that service to allocate the QAT cores that exist within certain types of hardware or certain acceleration pieces of hardware within the system. You can also interact with it in kind of a manual way. So this probably actually fits better with like the telco world, where you want to be really controlling around the latency of any kind of traffic flow that's going through these pieces of hardware. But in Ceph, the work that's been done has really been around the dynamic component, and we run the service on the operating system for that. So some history. QAT's been around forever. The first iterations of QAT, where it was a PCIe add-on card, they date back to like 2008, 2010 sort of time frame. And this was Intel's answer to how do you accelerate like a low-powered CPU. So Intel has obviously been trying to compete with things like ARM for years. ARM had this great idea of, you have a bunch of building blocks, you can choose how to put them together. This was kind of Intel's answer to taking something like an Atom chip, which is not very powerful, and start adding on these accelerators. Then we got to sort of the middle of the last decade, around 2015-ish, when Ice Lake came out. Ice Lake, again, not a super powerful, or Ice Lake D in this case, not a super powerful CPU, but they started to add QAT cores onto the die, so you could start taking advantage of that hardware. The compression stuff I don't think was around then. That's what's really appeared more recently in Gen 4, Gen 5 Xeons, so that's Sapphire Rapids and now Emerald Rapids. And what I'll talk about during this talk is how you can take advantage of that and make use of the compression elements. This idea of compressing data in a storage system is not overly exciting, but it can actually commercially be quite useful. So what has the upstream Ceph community done around QAT? There's a whole bunch of integration work that's been done so that you can essentially turn on these components to start adding in the benefits around server-side encryption, compression for things like server-side Rados gateway. Messenger can be compressed as well, and also BlueStore. The main area that I've been looking at over the last few weeks is around compression for Rados gateway. Of course, Rados gateway is sometimes treated as like this big dumping ground. Object storage is this dumping ground where we put stuff and we retrieve it later. So any kind of efficiency that we can take advantage of is super useful there. And the last piece around OpenSSL, we did look at this briefly, but this is really just the initial handshake. It's not the overall flow, so I didn't go into too much detail around that. So traditionally, and the reason why we never really wanted to turn on things like compression in any kind of storage system is, of course, there's an overhead. But what does that overhead kind of look like? So let's find out. So thanks to our friends over at Intel, they were able to set up this lab environment for us. So it's like a 4-node Ceph cluster. Each node has a pair of Xeon 6548 ends, so each one of those has 2 QAT cores. Not overly RAM heavy, for 8 OSDs, don't need too much RAM anyway, and everything was 100 gig networking. We were using 2404 LTS and also microceph, and the reason for using microceph, it's not a small scale Ceph, it's just easy to use. I'm a product manager, I don't want to sit and deal with complexity. The idea of microceph, in like 3 minutes, I can have a functional Ceph cluster. If I do something wrong, just blow it away, start again. It's super quick and easy just to interact with. So that was why I used microceph for this. All of the nodes had the Rados Gateway service running, and with microceph, it's like microceph enable Rados Gateway, done. Like you don't have to think about anything. The defaults are safe and sensible. And then we also had 4 worker nodes to use as our load generation. So for the testing, or some of the testing that I've been doing, I chose to use MinIO Warp. And I know some folks will be thinking, MinIO. But actually, Warp's pretty cool. This idea of having a bunch of different clients that run on all of the worker nodes, controlled by a single server, handles all of the concurrency, starts the test at the same time from each node, collects all the data at the end, summarizes it. You don't have to worry about collecting it from here, there, and everywhere. And also the fact that you can use a bunch of different workers to interact with a bunch of different Rados Gateway endpoints without a load balancer. For me, again, super quick and easy. It was a great way to kind of set this up and test things out. So during the tests, we were using the 4 clients, or the 4 workload generation nodes. Each node was set up to use each node was set up to use 32 concurrency. In some of my kind of what I felt like was destructive testing, I pushed that way higher. And the limits of this cluster were soon reached. There's not a lot of disks in there, and they're not the fastest NVMe drives in the world. But it was a great way just to see what happens when you kind of push beyond what's sensible, see where the maximal throughput of this relatively small cluster was. And in some of the tests, like the default in Warp is to write 2,500 objects to a cluster. That's not actually a lot of data when you use a 10 meg object. So pushing to larger scale, like 50,000 object tests, just to see how the cluster would react with a lot more data in the cluster, actually led to the same results. So it was a great way just to see how having more used capacity was affecting the system. And then these tests, in this case, it wasn't problematic. The one thing I kind of skipped over there was around the 10 meg object size. It's like a reasonable sized object. And I'm pointing out here that I was using the CSV object format. So initially, I was just using random. What was quite amusing was when I started to turn on the QAT pieces, I was like, hang on, why am I not getting any compression at all? Oh yeah, random means random data, which means not very compressible. So baselining that system, so the average read from the system was just over almost 22 gigabytes per second, with sort of an average CPU utilization of around 10%. And I'll go through these results now, but I'll show them in a graphical form in a second. It'll make it a little bit easier to digest. The average write throughput, 4.6 gigabytes a second. Obviously, the CPUs are working a bit harder when we're writing, so the utilization was certainly higher. Then we start looking at turning on compression. So this is compression with none of the optimizations enabled, so no QAT. And you can see we basically lost half of our read throughput and just over half of our write throughput. And of course, the CPU utilization has climbed there. With QAT enabled, we're back to where we kind of started. So we're a little bit slower for reads. The CPU utilization is a little bit higher, but that's kind of expected. You've got this extra thing turned on. What I found interesting was actually the average write throughput increased, because of course those underlying disks are now not having to receive exactly the same amount of data as they were before. So in sort of graphical form, over on the left there, the read bandwidth, no compression, that 22 gig number. We can see with the zlib algorithm, obviously there's that drastic drop with no QAT. Turning QAT on, we go back to kind of what normal. On the right side of things, yeah, you can see that same sort of pattern again with a slight increase for the writes. Looking at CPU utilization, with and without, so no compression compared to zlib with QAT, you're kind of seeing a very similar picture. The read side of things, we do see a slight increase there in the average throughput, the average utilization, but it's not something to be kind of worried about, I don't think. So just how effective is that compression? And this is, well, let's use the storage line. How fast is storage system? Well, it depends. What are you doing with it? What kind of data are you putting in there? So I used a bunch of, well, firstly, Warp itself. So with the CSV mode, you basically get a 25% saving, no real difference in the throughput. So that's kind of a positive thing, right? So in this screenshot here, there's roughly like a 400 gig data set. It's actually only using about 300 gig on disk, which is a significant saving. So that's synthetic data. It's all, it's just manufactured, it's tested. So let's look at some real world data sets. So thanks to the world of AI and machine learning, there's lots of data sets you can grab off the internet. So Kaggle hosts a bunch of sort of training data that you can use. And of course, we're in tech, it's the internet, cats, dogs, birds, kind of nice animals to store in a storage system. So taking 5,000 JPEGs, oh look, there's not a lot of space saving there, because of course the JPEG's already compressed. So not a huge saving. Is it worthwhile if you have a very image-heavy data set? Probably not. So what are the data sets could we look at? Some research data. So back when COVID-19 was kind of a thing, I can't remember the name of the organization. It's the Allen Institute It's the Allen Institute, let's leave it as that. They provided a 100 gig data set of research data, and they kind of challenged folks in the machine learning community to use that to mine the data, to go off and make more informed decisions around the COVID-19 stuff. So that data set's a bunch of JSON, a bunch of CSV, a bunch of textual data, and pretty good savings there. 24% saving in a storage system is it's pretty significant. So keep scaling that up. It's super positive. YouTube, they also publish a bunch of data sets that you can use for kind of any purpose. If you want to use them for training, you want to use them for testing compression, like I did. So they have it's a 2 terabyte collection of data. The machines I was using didn't have loads of local storage, so I just grabbed a couple of 100 gig of that data to see how that would react in the system. And the savings here are pretty cool. 68% saving on raw video files is an awesome saving. We opened our London office earlier this year, and we have this quite fantastic AV setup there. An hour's video from that setup's like 1.5 terabytes. So when we did Ceph Day there, we had like the entire day recorded from 6 different camera angles. There was a lot of data, so this kind of thing actually could be kind of useful for us internally. Never mind like actual other sort of production use cases. Of course, something like H.264 video files. Yeah, there's no space saving there; it's already compressed. So your mileage does definitely vary. This is all with a mindset around object. But what about RBD? What about Cephfs? So this is not super detailed, but I did also take some of those same data sets, drop them into RBD volumes just to see, again, how things would kind of react. And you can kind of see there the RBD compression pool, that had a volume on there that was that same raw data from YouTube. You're seeing quite a significant saving there. The COVID-2 pool, I can't remember why I called it COVID-2. Maybe I messed up something with the first COVID pool I created, then called it COVID-2 because it's easy. That pool, again, it's that research data, all very textual, very compressible. So you see those, the same compression behavior even for RBD. And this would also apply for the underlying pools for things like Cephfs as well. So the results kind of mixed. It very much depends on the data set. This is where I switch into my previous operator, product manager mindset. I think, what's the value here? So what about the cost? And I'd start with a question. What's the most expensive thing in a storage system or in a storage node? Well, it's not the CPUs. It's not most of the hardware. It's actually the disks. So this is a list price. Don't panic too much. No one pays these prices. But this is, if you go and price something up, you want to do a fair comparison, you kind of have to use list and not negotiated discounts. So yeah, just over $9,000 for a 15 terabyte NVMe drive feels onerous. And then if we build those into a couple of comparable configurations, so over on the left we have kind of my favorite machine, a 2U server that takes plenty of storage, is actually quite adaptable between an NVMe use case. Could also be configured to be a high capacity node as well, using nearline SAS or SAS disks. So pair of the same Xeons that we had under test, a little bit more RAM because there's more drives in there, perhaps maybe even a bit light on RAM in this config, but that's kind of fair. We use the same amount in both, or I use the same amount of RAM in both the comparisons. 100 gig everywhere because, well, why not? And then just a simple RAID 1 pair of NVMe drives on Dell's boot. Dell's Boss boot add-in card. So again, list prices. These are not, they would be comparably discounted if you were to buy either of these configurations. Over on the left, with QAT, $240,000 a node. Sounds scary. Without QAT, $242,000. So what's the difference here? Like $500 per node? That's not a lot more to spend when you start to think about the savings that you can get with these different kinds of data sets. So if you do have something that's even slightly compressible, you're getting something kind of for free here. So if we look at the per dollar comparison, we have this nice linear kind of discount as you start to increase the compression levels. And of course, to believe that you might be able to compress all of your data at 50%, that's probably not sensible to plan for. But if you think, oh, maybe I can get 10, 20%, that's actually it starts adding up quite quickly. If I think back to a previous company I worked for, we used to operate a managed services platform. And back in that time, we were kind of scared by things like thin provisioning. But as you have a system for a number of years and you have thousands of customers using it, you can start to build out a model of how people use that system, how they consume capacity, what the actual overall trends are, so you can kind of plan ahead. So if you have data already today, you can take a sample of that. You can look at how well it can potentially compress. You know your consumption rates, so you can kind of plan ahead with some idea of maybe 20% compression. So you can see that going from that like $1.90 down to like half of that, 95 cents per gig at 50% saving. That's pretty cool. I feel like I've gone through these slides rather quickly, but if this is something that is kind of interesting, definitely try it out. And like the easiest way we believe to try out Ceph is using microceph. You know, it's this quick snap install microceph that gets you the snap gets it installed. You also need to add the QAT engine as a service on the machine. Something I forgot to do and couldn't understand why it wasn't running. And then kind of went back, reread the documentation, realized, oh yeah, I need this service running. We have to interact with the thing, right? Bootstrapping microceph, single command, adding nodes, depends on the number of nodes. Adding disks is like, you know, give me all the available disks in the machine, and then this single command of enable Rados gateway, and you have, you know, this functional system. Turning on the QAT compressor, again, it's this single like config setting. It's like, you know, you have all of these pieces in place. Turn it on by you know, setting that variable to true, restart all of the daemons, and then you have compression enabled in the system. One more step is adding or modifying the zone placement so that you have a storage class associated with using zlib. And then, oh yeah, the one last thing on here, we're currently installing the snap using dev mode. So dev mode basically allows us to interact with any other service or any other interface within the operating system, within the machine. We have recently added into snapd an interface that allows us to interact with the QAT engine. So we won't actually have to do that sort of dev mode hack or cheat very, very soon. And so the kind of takeaways here, you know, I think it's kind of, the first one's very obvious. You know, I think everyone realizes that compression does depend on the data set. Is it compressible? Is it, you know, already compressed when you're writing it to a system? And of course, you're not going to get any benefit there. But if it is kind of textual, if it is, you know, lots of unstructured data, there is potential for compression savings there. So with the, you know, even 10 to 20% compression savings, when you start factoring that in as to what the underlying disks actually cost, what the nodes cost, you start seeing some quite compelling savings. The performance, as you could see, was actually surprisingly comparable and quite equivalent between the two configurations by turning on the QAT pieces. And then, of course, it applies to all media. You know, in these tests, I used NVMe devices. We wanted a relatively fast cluster just to see how far we could push things. But if you had, you know, high-capacity, dense machines, again, the same savings would apply in terms of usage of raw space. And finally, I just want to acknowledge a few folks who helped us out with all of this work. So Boon Tan, over at Intel, he looks after one of their lab environments. The lab we were using was on the west coast of the US. I'm based in Germany, so lots of late evenings while we tinkered with things, and I broke stuff, and he fixed it for me. Gufeng Tang, he was leading the Intel Ceph team. He did lots of work, and his team did lots of work to enable QAT within the operating system and also within Ceph itself. And of course, my wonderful team who created microceph, and means that someone like me who's not that technical anymore doesn't have to worry about too much detail and can have these quick sort of repeatable deployments of Ceph without having to think too hard. And with that, thank you very much. Does anyone have any questions? And also, we are hiring, so if you're interested in joining Canonical and working with Ubuntu and Ceph, please find me.